Hi, my name is Naga. I'm here today to explain our robot software implementation. When I first started, I had no idea how I was going to do any of this. And since we're new to this, we asked our predecessor Mark, who attempted this competition back in 2012. Mark was kind enough to give us the old robot and let us mess with it. Unfortunately, the robot itself was missing parts. Most of the electronics were taken out, and only the motors remained on the robot. The robot itself was used as a display model and over time had suffered from metal fatigue, so the frame was not reusable. So in general, the old robot didn't really help, and in order to get a handle on the situation, I read several autonomy journals which are referenced in the systems engineering paper. And using what I learned from those articles, we developed a system for this competition, and hopefully it works. The interfaces used on this robot particularly are PWM, SPI, analog, serial over USB, and I2C. The brain of our robot is a small Linux machine called the Raspberry Pi 2. The Pi is connected over these various sensors to do its general thought process and compute an automated path for collecting the dirt and coming back. Some of these sensors are actually fed through an Arduino and then to the Pi. This is done because the Arduino itself can control several PWM devices while the Pi can only handle one, and it would consume the Pi's processor consumption, so it was not an option to use the Pi to control PWM devices. As for the robot itself, it contains a two-channel high-amperage motor controller that drives these four motors that drive the robot quite literally for moving. It also has a 4-channel relay that controls both this motor up top and this motor driving this digger assembly. And the 2 channels are dedicated as an H-bridge to allow these 2 linear actuators moving this digger assembly up and down to move forward and backward. And the Arduino is connected to this relay, this 4-channel relay shield, to communicate, and is also connected to the motor controller, which is acting as a which the Arduino itself is acting as a pass-through between both the motor controller and the 4-channel relay to the Pi. And the Pi sends the appropriate commands to the Arduino. And then we have two optical sensors on the roller of these giant tank assemblies. One on this side, one on the other side. And what these optical sensors do is help us calculate distance. And along with the gyroscope in the middle of this robot, these sensors are used together to provide a correction for the distance from our target. The actual distance measured from our target is measured through a color sensor called the PixieCam. There's a LED that emits a green light to help increase visibility for this target, and the PixieCam picks up the object and calculates the distance between the camera and the object. The gyroscope and the optical encoders are there to act as a dead reckoning system to fix any errors between the PixieCam and the target, because at some points while moving, the PixieCam will no longer be able to view the target just due to the fact that driving out of visibility range, or driving really into non-visible spectrum, because we won't be able to see the target when we have to dump, and that's why those two are used there temporarily as our distance sensors. Another thing that we use is the LiDAR sensor, which operates over USB and is connected to the Raspberry Pi directly. And the LiDAR itself is used to detect obstacles and potholes. The way the LiDAR does this is, over a small distance, it checks for the change in height. If the change in height is exceeding a maximum value, whether positive or negative, it will treat the object or that area as an obstacle and tell the robot to rechange its path planning for moving around. and our Pi itself communicates to our laptop when in manual mode over multiple sockets for the various sensors, so we can read the input and determine the actual path that it has to go. But when in autonomous, it pings a packet telling us when the machine is operating, and it minimizes the data usage while in autonomous, actually, when compared to manual. We use the Mars rover lander camera just as a support system to verify the system is working, because this is our first attempt still, and we want to just be safe on that side, and that's why we use the lander camera in our simulation. But the Pi itself is also data logging all the sensor data into Excel-like files for later usage and analysis. So that will help us figure out any noise canceling algorithms and stuff like that down the road for next year's competition. But this is an actual map in the Pi fed represented by a two-dimensional array. The map itself is slightly smaller than the field to prevent horrible collisions with the walls that create horrible scratching sounds like some spiteful teacher that just wants to kill your ears by scratching like a chalkboard or something. But we made the map smaller just to avoid that terrible sound. But and also the fact of the matter is these walls are unusable and we cannot use these walls anyways, so why would we want them in our field model at all? Because as you state in the rules, we can't have walls, so remove that from the equation. And after the robot is connected, and a go command is sent from our machine to start in autonomous, the robot actually will look for the target. The target itself is this red object. As soon as it finds this red object, it will put it into this virtual map. And, well, it won't put the object into the virtual map. The actual robot gets placed in the virtual map. This is preset by us on the collector bin. The target itself is preset. And the robot, based off the target, is able to use the target as a landmark and find where it is and rotate itself into a starting position for it to start in autonomous. Which it does. After doing so, it uses those green squares on the corners to help do all that. And after calculating all that, it sets up the rest of the map and creates the path. This pink area here is where it will actually dump, and when I was talking earlier about the camera losing vision of the target, it's right around this area where we start relying on the gyroscope and the optical encoders to do their job. It's because at this point, some point around here, within these last two rows, or columns, rows, it won't be able to see the target just because it's too close. But that's what I was talking about. As soon as it rotates, it'll move forward into the next section and remember the point it entered from, which is why this whole brown lines here is saying at any point on this, in this specific row, keep the entry point, and we will reuse that later to re-enter back into here. After getting past it, the robot itself will navigate through the obstacle course. What it does is it saves the path it walked upon as purple squares, or in our case in the two-dimensional array some arbitrary value, whatever that value is, and the robot will move along based on a forward path. It will try to look forward, or it will move left or right based on the obstacles it encounters. In this case, it encounters one very large obstacle, might possibly be the huge crater that is referenced in the paper. May not be, it might be several of those larger rocks that are randomly placed. But it detects an obstacle and it says, okay, you can't go in this area, and creates a new path to walk around it. After walking around it, it will save the point of entry and save this path taken as this purple value, whatever that value be. After coming into this point of entry, it goes from wherever it entered to this specific point on the map. This specific point will actually get updated by the number of runs it does, but on the first run it will go to the very edge of the field and it will start mining out this black area until it's full, or until it reaches the end of the row, and at the end of the row it will actually go back to its starting point, or even during mid-mining and it finally finishes mining and collects enough regolith that it can't hold anymore, it will go back to the starting point and follow the path taken back. As so. Back into that dump area. Once it hits the starting area, it calculates the path to the dump area and goes from there. And it repeats the cycle several times until 10 minutes are over, or the command to stop autonomous and go switch to a manual are given, or just to stop in general. One of those three things will have to happen for this thing to shut down remotely. Physically, you can shut it down by hitting the large red button. But other than that, that's the general idea of our software. What it does is create this virtual map and navigates the robot based on the map provided. And that is all this robot does. And that is, these are the two references for our wheels. And that is all. Any questions? Any suggestions? If not, have a pleasant day.